Hello and welcome to my channel. Today we are with part 2 of computer experiments using numerical methods in ForTran. And as you know that in our first video, part 1, what we did that under the heading of the different experiments, we tried to give the physical problem and then the mathematical problem associated with that physical problem, and then of course with the help of numerical analysis how to get a computational task, that is a computational problem, and then we have visited the program closely, including the programming logic, input, output, and finally if there is any conclusion. And in part 1 the experiments, the numerical analysis, we assume that in this discussion we will not be discussing numerical methods in details because it will corresponds to the theory part of the corresponding paper. So in part 1 we have discussed two experiments actually. Both are of the same type, roots of equation, finding roots of equation by an iterative method, Newton-Raphson. And the experiments was volume of Van der Waals gas and pH of a weak acid. So today in part 2 we will be visiting a few more experiments under the category first experiment 2, numerical differentiation. Under that there are two experiments, change in pressure for small change in volume for Van der Waals gas, and the second one is Potentio-metric titration, or equivalently pH-metric titration we can say. And that is experiment 2. And the third experiment, there are three experiments, but the category is the numerical integration category, either by Simpson's 1/3 rule or by trapezoidal rule. And the experiments, entropy change for heat capacity data, from heat capacity data, enthalpy change from again heat capacity data, and probability distribution, kinetic theory of gas, and corresponding mean values using those distribution functions. So that are the tasks today. So we'll start with numerical differentiation experiment 2A, change in pressure for small change in Van der Waals gas. So the physical problem looks like that. What the equation everyone knows, that P plus A by V square into V minus B equal to RT for 1 mole of gas. So you can little bit manipulate to express P in terms of V as RT by V minus B minus A by V square. Now if you differentiate dp dv, then you will get theoretically minus RT by V minus B whole square plus 2A by V cube. But our task is to evaluate this derivative dp dv at different V numerically, that means using numerical differentiation scheme, and of course we will be comparing those values with the exact theoretical values obtained from this expression. So we will be using the differentiation scheme like this. The first derivative formula looks like simple. The function value at x plus h minus function value of x minus h and divided by 2h, where h is the interval between two consecutive x values. And this is the second derivative that would be required in our next experiment. So let us have a look on the program that we have used for evaluating first derivative of pressure with respect to volume for Van der Waals gas. So here this program, I would just analyze a little bit of this program. Here some of the inputs are there, so you have to initialize the first x value, I mean here in program x, that stands for volume, and then how many points that you want to calculate, the interval h 0.005 is small one, and then in an array we are developing the array XA within a loop. XA, that means different volume, right? And we have got it by adding an increment of h in every step, and then we are calling the subroutine subprogram, and that is fxcal, and the input is x. Here x is nothing but the v, and then it calculates fxv, that means the function value at that given v, and then the exact derivative value from the theoretical expression. And here we are implying, I mean, we are using that differentiation scheme, numerical scheme, as you understand that f or y x plus h minus y x minus h. So it is fx I plus 1 minus fx I minus 1, because it is inside a loop I. So I goes from 2, 3, dot, 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 divided by 2h. So this red portion is actually translating the numerical differentiation scheme, and then it's writing the x value, the function value at that x, that means p, pressure, and then the first derivative, and then the exact value of the first derivative. So that would be visible from the output file. So now how exactly we do evaluate all those required things in the subroutine. Its name, as I mentioned, fxcal. I'm calling it in the main, and this is the subroutine which uses all the parameters a, b, r, t, all are given for a given problem. And then fxc is, you see, these two things. Fxc, that means the function value at a given v, and that is rt by v minus b minus a by v square. So this formula is translated in this expression, and the next one is the theoretical exact derivative expression translated again in this ForTran expression. So this is how we evaluate in the subroutine. So now let us run the program for evaluating dp/dv for Van der Waals. Well, this is the program. As you see that the three input recommend, and now let us run the program to see the result. And remember that we will get the output from the output file. So what are the inputs it is asking for? So you see that it asks for x0. So let me give you 0.07. Okay, 0.7, and then 50 points. Let me try it only 50 points, and 0.005 the interval as I shown it. Well, the program is executed, but it is not showing anything on the screen because I have to open a output file there. So you have to open the file der, and then you will see the results. So as I have put n equal to 50 and x0 is given as 0.07, and then it at an interval of 0.005 it gets the v values, it evaluates the p, that is the function value, and then it evaluates the derivative values and the exact derivative values. Okay, and the interesting point is that during the course of that whole range of v, p as a function of v. If you plot the Van der Waals equation, there is three different regions. First the slope is negative, then the slope positive, and then again it becomes negative. So that we will see from the results as well. So that's the result. Let us have a quick look on the result itself. So we have used some Van der Waals gas with constant A equal to 3.64, B is this, and we have taken temperature to be 273 Kelvin and R in liter atmosphere unit. So initial V is 0.07 and H is 0.005. So here the blue color is that the first one is also negative slope, and then the black ones all are positive, and then again in the later part we are again getting the negative slope. That means the first derivative dp/dv. So that is the first derivative, and they are the dp/dv exact. So as I mentioned here, all three regions of negative slope followed by a positive slope and then again negative slope are covered. So that's all about our first experiment 2A. Now we are switching over to experiment 2B, pH or potentiometric titration. How we can evaluate the required values. So let us see the program first. So it is mentioned that it is the derivative and the second derivative as well. So here we will be using both the first derivative and second derivative formula. Here the difference with the earlier program, that it was an analytical function, p as a function of v was given, Van der Waals equation, but here we will be getting all those y values, that means x versus y values, and they are the potential value for potentiometric titration and pH value for the pH metric titration. That means the y values we will get directly from our experiment. And of course, there are some discrete values, not continuous something. Okay. Again, we are in need of a file, Part-out status new, that means the output file. And in this loop, again you see the first derivative formula, fi plus 1 minus fi minus 1 by 2h. So this formula is translated in this line, and the next line is standing for the second derivative. You see this formula is translated in this format expression. Some h square is there. So that's all about something to say about this program, and then let us run the program. So program, and here you will see that no input as such is required, all are given inside the problem, and that's why it is straightforwardly giving you the result. But as I mentioned, the output that you can see from another output file, and that is Part-out as I have shown. So let me call the Part-out, that is the Part-out file. So a different, if you can say, number of drops, and then the EMF as recorded from our experiments, and the derivative and the second derivative. So you can have feelings that where exactly the utilization point is there, because in the second derivative sudden change, appreciable big change is here around point number 10, that is the potential EMF value 4.9, and that is apparent from the first derivative data also. So that is how we can use the numerical differentiation scheme for this kind of titration, potentiometric or pH-metric. So now let us go for the pH-metric one, and we will not go into the details of this, but if you see, the results are like this. It is pH-metric, and this is as I have run for potentiometric, so around 10.4.90, and this is for pH-metric, another that I have not run, but all the same, the logic is all the same. So now we will be going for our almost last part, that means numerical integration part, either by Simpson's or Trapezoidal rule. But there are 3 experiments, so one by one, let us see quickly the experiments first. Entropy change from heat capacity data, right? So the physical problem, the physics behind it is like that you have a formula for evaluating delta S. Delta S over temperature. That means initially it is A and B at the lower and upper bound of temperatures. That means TL and TH, lower and higher temperature. And the function is Cp by T dt. Of course, Cp is a function of T, A plus Bt plus Ct square in joules per Kelvin per mole. So the whole integration Cp by T is a function of T, and you are integrating over T over the range A to P. So that's clearly an integration problem, and that you can do numerically. So the input for a particular given problem taken from textbook, McQuarrie-Sherman, I have used this dependency of Cp on T, A, B, and C like this, A, B, and C, and the lower temperature is 300 Kelvin and higher temperature is 1200 Kelvin. So as inputs, we have used 100 number of points as part of our programming numerical method. So the results, first we will have results, then we will show the program and probably will run it. So the result, the reference is McQuarrie-Sherman, page 257. Now you have used both the trapezoidal and Simpson's rule, and results are very close but not exactly the same. And the reference, that means in McQuarrie-Sherman, the result is evaluated to be 44.73. So again 70, 70. So they are very close. All of them are very close. But now we will be showing only by Simpson's rule. Trapezoidal rule, I will use it for another problem. So either you can use Simpson or trapezoidal, no problem. Okay. So let me go for the second problem, 3b. Before we run, finally, let us go through all the three problems on numerical integration. So the first one was on entropy change, and I have shown how the formula we needed. And the second one again, enthalpy change, again from heat capacity data. So a particular substance, okay, enthalpy or heat content of that substance at higher temperature Tb and lower temperature Ta, that is given by this integral Cp dt. Now Cp is again a function of T, a plus bt plus Ct square form of function. So the thing is that if you know the H at a lower temperature, then you can evaluate the H at a higher temperature, provided you know the temperature dependence of Cp of that substance. But that is only for a given substance at two different temperatures. So not much of chemical information is obtainable from this kind of problem. Rather, it is more relevant in a problem like this. That again, it's, you can say, enthalpy change from heat capacity data, but this time it is not of a particular substance, but rather a reaction. So heat of reaction, we call it heat of reaction. Delta or heat of formation, you can say here in this case, because ammonia has been formed from nitrogen and hydrogen. So delta FH standard condition at a given temperature, say 25 degrees centigrade, it is known. Right, now we have to evaluate to find that same heat of reaction but at a different higher temperature, 1000 Kelvin. So what is the working formula for that? Again, it's, as you know, it's in thermodynamics we call it Kirchhoff's relation. So delta FH at higher temperature is equal to that same at the lower temperature plus this integral delta Cp dt. So it was Cp dt, but now it is delta Cp dt. And Cp is A plus Bt plus Ct square for each of the species, ammonia, hydrogen and nitrogen, and the coefficient 3 by 2 and half is there. So delta Cp you have to evaluate accordingly, and from our text the examples we have taken for ammonia synthesis, hydrogen, nitrogen and ammonia, the A, B and C are given for each species, so we can evaluate the delta A, delta B, delta C kind of thing, including the coefficient, 3 by 2 and 1 by 2, as you know, the stoichiometric coefficient. This x can be A or B or C. So finally, if you evaluate delta A by using this formula, you will get like this. That means these three values you use along with this coefficient properly. So you will get delta A, delta B and delta C like this. Now you have to evaluate delta Cp. So that is nothing but delta A plus delta Bt plus delta Ct square. So if for a single substance it was just A plus Bt plus Ct square in this Cp, but here it is delta Cp in the formula delta Cp, and naturally delta Cp is not A Bt Ct square, but rather delta A, delta Bt and delta Ct square. So in the program all are evaluated using these values taken from the text, and the output and input are like this. So it was the problem. This is called the integral, and the lower that is known to me, and that is the unknown that I had to find from this scheme. So lower temperature is 298 Kelvin and higher temperature is 1000 Kelvin for this given problem, and we have used only 100 points, and the initial point is also given, that is at this temperature minus 46.11 kilojoules per mole. So the integral, that means this evaluation of this integral only by different scheme, Trapezoidal, Simpson's, and that from the reference cited are very close, 9.75, 9.82, 9.75. And finally, after adding this quantity with this integral value, that means these values, we get the final that we are asking for, that is delta FH naught at 1000 Kelvin, right? So these are the values, and again you see they are very close, minus 55.86, and again this is also 55.86 by trapezoidal group, and Simpson is slightly added. So that's an excellent demonstration of this numerical integration scheme. And the last one, this is again from our physical chemistry preliminary courses, probability distribution, kinetic theory of gas and mean values. As the first year students, they come across this formula, f ux in one dimension velocity distribution function or in three-dimensional speed distribution function f of u, and it's an energy distribution function f of e. Of course, the range, if it is one dimension, then it goes from minus to plus infinity, but in the other two cases, it's from 0 to infinity. Well, these are the probability distribution function, or simply distribution function, and the average of any other quantity. Of course, that quantity is a function of this u or ux or epsilon, and average of any quantity q can be given by this formula, where it uses this distribution function f, this distribution function, and the quantity that you are asking for, the average of which you are asking for. So q into distribution into du, and then over the whole range of variable. So that gives you the average quantity of q. So that is the average definition, standard definition. And here you please note that this distribution function, we call it also probability density, this fux or fu or epsilon. So it is probability density. Now when it is multiplied by the volume element, so volume element, some d tau or dux or du or d epsilon, whatever it is as per the problem. So the density multiplied the volume element gives you probability in that small volume element, and when you integrate, that means you are summing up the probabilities over small portions, that means we are getting the total probability, right? So as per the probability rule, the probability total is always unity. Whatever the distribution function, if they are probability density, then of course the total integration result must be 1 unity. And here it is represents some real substance, gas. So whatever the mass of the gas molecules or whatever the temperature you take the system, it doesn't depend that this integration result must be unity, right? Because it represents a total probability, and in other way it is the area under the curve. Okay. So of course we will verify this numerically also, along with the different average quantity verification or evaluation. So for example, we know that if you use the distribution function, we have discussed three. One is fux, another is fu, another is fe. So average energy you can calculate using fu, three-dimensional speed distribution function. We can evaluate either the u average or u square average, and similarly for one-dimensional distribution function, you can evaluate either ux average or ux square average. And from our theoretical understanding, we do exactly have the exact expression for all these average quantities, and the results are the first one is 0 because it's a symmetric distribution curve, Gaussian. So average naturally would be 0, but ux square average is given by RT by m. That depends on what t and m you are taking. And similarly, u average, that also u square average and energy average from our theoretical understanding. But what would be our task today is to evaluate these integrals one by one, or maybe all in a single program, and to verify those results, evaluated results or other computed results, with this theoretical exact results. So we will be using trapezoidal rule for this problem. And before we go for running the program, let me just show you the results that we have already got. We have used the carbon dioxide gas, that means the molecular mass 0.044 kg per mole. Temperature we have used 300 Kelvin, and we have used trapezoidal rule to find the different mean average values as well as the area values. That means the in quantum was as normalization, kind of normalization. So ux average, it's supposed to be 0 as I mentioned, and we are getting 10 to the minus 6, or we can even improve this result even better. So it's a very small quantity, we can treat it as 0. Then ux square average, you see the results are almost same, the theoretical and the computed by our scheme. U average similarly very close, U square average and energy average all are very close. the theoretical and computed values. Not only that, we have used the area calculation, that means that simple integral if ux or fu or fe, whatever it is, and then the volume element, and that area or the total probability is supposed to be 1 theoretically, and we are getting okay, all are very close to 1, right? And you can even further improve the result. But one question I must raise separately, that in some of the cases, you know, when you are going for integration, you need a range, and that range for this distribution function goes from minus to plus infinity for 1 dimension, and for 3 dimension it is 0 to infinity. So computationally in our program, the question is how to manage plus minus infinity. That's a big question. So we'll come to this point later on. Okay, so the scheme, we are basically will be evaluating this kind of integral, and the Simpson rule, as I've already mentioned in the first lecture, it translates this formula only, and trapezoidal is very close to 1, this another formula. And then let us go for the logical flow of the program. So we'll be showing the delta S calculation, delta H calculation for formation for ammonia reaction, and then we'll be using a 1-dimensional distribution function. So we'll show that we have already shown the results, but we'll run 1 or 2 program, and before that let us quickly see the logical flow. Okay, so you have to read some of the system parameters. Say in the earlier delta S or delta H calculation, you need the temperature dependence of Cp, that means through A, B and C. So that are the parameters. And in the last case, it is the mass of the molecule, molar mass, or the temperature. These two are the input parameters, right? And then you have to read the limits of A, B, right? Lower and upper limit. So you have to read the limits XL and XH, low and high, and then you have to take the number of points in your integration scheme. As you see, this y1, y2, y3, y5. So how many points you are using actually? That is you can play with, and then after getting the higher and lower limit, you can evaluate the interval H, that means higher value minus lower value divided by number of points. And then you see in both the formula you need y0 and yn, right? y0 and yn. So we need to evaluate y0, that means the function value at the lower limit xl and the function value at the higher limit xh. So that is needed, and then for this series of terms, this one, that one, or this one, we need naturally, if it's a repetitive summation, then of course in our language we need a do loop, right? So do now you see I over odd 3 to n minus 1, odd because you see in trapezoidal or Simpsons, it is a separate series 1, 3, 5 n minus 1, which is multiplied by 4, and another series the even indices 2, 4, 6 dot dot dot, but that is multiplied by 2. So we will be separately doing this 2 summation, and then accordingly we'll multiply by 4 and 2 respectively. Though in trapezoidal all are multiplied by the same multiplied 2, but that's not a big problem. So in general we'll be doing separately. One is over the even and another is over the odd. Okay, then evaluate I, that means the integral. So if it is trapezoidal, then we'll be using both the sum and then multiply by 2, and if it is Simpson, then we'll take separately the 2 summation, one from the red region and one from blue region, and multiply by 4 and 2 respectively, and then finally we'll add y0 and yn in both the cases, and finally we'll be multiplying by h by 3 in one case and h by 2 in the other case. So by that way we can evaluate as per the problem. Now the program for delta S evaluation by Simpson's rule. So nothing much is there to say about the program. I have already explained, but still a few points. Here x is xl plus h, and xl is the lower point. So that you have separately calculating y0 at that xl point and yn at xh point by evaluating in the sub program fx that we will see later on. Well, and then it goes for a loop. You see it's a blue color separately used, different color, and it takes x plus 2h. That means it jumps 1 point because it is the 1 3 5, so jumping 1 point, right? So that's why I'm multiplying 2h, and every time it evaluates x and it comes in the fx, that new x, and it calls the sub program fx and it gives you back the c. So that we'll see what exactly is being done in the subroutine. And here again the green color, the same kind of thing, but it is xl plus 2h, the second point, because it is the 0 and then the first one is used here, and so the second point, and then skipping again 1 point each time. That means again it is plus 2h. So every point it is adding, we are adding 2h, but the starting point is xl plus 2h itself. So we are getting the even point here, and then the finally you are multiplying by 2, but here you are multiplying by 4, trapezoidal and Simpson, and then we are finally adding y0 and yn, and then getting multiplying by h by 3, we are getting finally the sum, and that is the integral, the sum. So that is the integral. Okay, and what we are doing in the function subprogram, it is simply evaluating the function value at a given x, and that we are calling it fx. So a, b, c are the input, and x is the input, another input, and the output is communicated back to the main program by the name fx itself, and fx is nothing but a plus bx plus cx square. Okay, so now let us run the program number 5, that is evaluation of delta s program. Okay, so let us run the program, and this time the input, okay, let us see what the input it asks for, and how we can see the output. This time we have not opened any output file, so the result is supposed to be on the screen. So okay, it asks for the n, that number of points, so I am just using 100 points. Okay, and then the lower limit, so 300, and the higher is 1200. So that means at 300 Kelvin the data is given, that ABC, and we are asking for the delta S at 1200 Kelvin. So you see the result is coming as, so the number of point n is 100, h is okay, interval is evaluating, and it is coming as 44.7306. So this is the delta S, right? So now let us see that, go back to the result that we have already actually seen that. Okay, if you go back to the result, then you can go back actually. Yeah, I have to come back a few slides. Here you see 44.732456. So this is the result, and that does match with the exact value from the Macquarie-Shannon text. Okay. Good. So let us go for our last part, the last experiment, and that is the program for 1D velocity distribution using trapezoidal rule. So we have already discussed the physical problem, the corresponding mathematical problem, what we really want from our scheme, and what are the results, and the beautiful matching between the computed values and the experimental, theoretical exact values taken from the text. But now one thing is left only, that will be running this program to see how really it works. So just a few words from color separation. You see that I am calling a subroutine subprogram, right? AM is mass, T is temperature, and then CL is the lower limit of temperature, and here again it is calling, and this is CH. So CL and CH, that is the lower and upper temperature. So temperature is the input for this subroutine, and then it is 3 colors are there, green, red, and blue. So FC, FC1, and FC2. Actually, it evaluates at the given temperature. FC is the value of the function fu or fux. Here it is one dimensional, so it is fux. This function itself is the fc. Now fc1, when this function is multiplied by the velocity, that means we are going for the velocity average, and fc2 is the function, distribution function, multiplied by c square. That means we are going for finally the c square average. So the first fc, actually it will give you, when integration would be evaluated, it would give you the area. So we are expecting a result 1 for that portion, and fc1 is the average of ux, and that is supposed to be 0 because it's a Gaussian symmetric around 0 curve. So average is supposed to be x equal to 0, and then the ux square average, that is not 0, and that will be given by a formula that we have already seen. So we will run the program, and then we'll check that how far our computed values do match. So here again we are using that y0 and yn, two values we need for our integration scheme. So y0, the green color, at one is at a lower temperature, another is higher temperature. Similarly, yn and at the first fc1, that is u, when you are calculating the u average, and then we are calculating the u square average. So 3 y0 value and 3 yn values, right? And then we need the summation part, right? Summation part, and that is being managed in this loop. So again we are initiating 3 empty box, sum, sum1, and sum2 for these 3 quantities, and then we are giving the increment to the c value, and c is the input here, and then 3 different color again. So sum is sum plus fc, that means this fc part is being added one by one after another to the same box sum, and then fc1 is being added, fc2 is being added. That means we are doing 3 summation, right? And then we are finally multiplying by 2. In each case it is 2 because it is trapezoidal, but in Simpson we have to take it separately and multiply by 2 and 4 separately. But in this case, in trapezoidal case, we have taken all the terms summation together and multiplied by only 2 in each case. Okay. So here you see sum 1 is y01 and yn1. That means the 0th point y0 and yn are also added and finally multiplied by the some factor was there, m by 2 pi kt, etc. So we are multiplying by this factor and finally getting the sum 1, sum 1, and sum 2. So we are writing that, as you see, sum 1, and sum 2 as the 3 integral. 1 stands for the area, and which is the predicted value we have written here 1, that we know. And sum 1 is the average. For the one dimensional case, it's supposed to be 0, and sum 2 by the exact formula it should come as RT by M. So it will evaluate RT by M and will show the result. And the sum 1, sum 2 are the results that we are getting from our integration. So these two should match. These two right statement, the results, they should match, we are supposing. Okay, this is the subroutine fcal that we have been calling it number of times. So the parameter r is given, and you see this is mc square 2rt and e to the power minus this ff. That means we are evaluating e to the power minus mc square by 2rt. That is the function itself, and then fc1 we are multiplied by the function fc by c, and fc2 we are multiplying the distribution function fc by c square, as I already mentioned. Now the same question, how you really manage plus minus infinity, because you have to give the limit, you know, CL and CH, two limits you have to provide to the computer, and that is a matter of your experience, that if you play with that, you put some CL is say minus 100 and plus 100, then you will not get the result properly. So it should be big enough. So for computer, according to a problem, infinity is taken in a way that it should be big enough for that purpose, for that problem. So in our case, my experience, I have played with these values. I have done with -100, -1000, -2000, and I have seen that okay, -2000 and +2000 as the lower and upper limit are good enough as infinity. And of course, the number of points you can increase or take a little bit less, no problem. So n is 1000, lower limit that is ux is -2000, and ux upper limit that is plus infinity is again 2000. So now we will be running the last program of our discussion. Well, this is the program. We need a pi, the factor. So let me run the program. So it is asking for n. So as I have told that it is, I will give 1000, and then minus 2000, the lower limit of that is minus infinity actually to the computer. In this problem, 2000 is the plus infinity, and we are interested in a particular temperature, say 300 Kelvin. So let us see what are the results. So here we have no output file. It is all the results are being visible on the screen. So the predicted values are integrals 1, 2, 3. So the first one, as I mentioned repeatedly, that it represents the area, that should be 1. And the second one is the average of ux. For one-dimensional case, it should be 0. And the third one is ux square average, and that is RT by m. So by that formula, the evaluated exact value should be like this. Now this is the last line, predicted values. But what the values we have got from our program? You see, the first one is 1.000000. So at the 7th place, something is there. So I think you would agree with me that we can treat it as 1. And again, the second value is supposed to be 0, and of course, it is a very close, very small value, 10 to the minus 6. You can improve the result by increasing the number of points, etc. And interestingly, the third one, that is the ux square average, you see 56686.36. So 56686.359. So how close they are, excellently, beautifully, they are very close. So that's I think all about our last program that we have run. So today we have run program 3, 4, 5, and 6. One is for DPDV $5 gas, and then the potentiometric or pH-metric titration, that is the numerical differentiation part. And then in the third part, numerical integration part, we have run one program for delta S calculation and one program, the sixth one, for average calculation using the distribution function for one dimension. So wishing you all the best, and thanks for watching. Thank you very much.